morning. I'm Devasena. In this lecture, we are going to discuss about ideal and practical transformer phasor diagrams under no-load conditions. This topic is present in the subject Electrical and Instrumentation Engineering. Concept of ideal transformer. A transformer is said to be ideal if it satisfies following properties. First one, it has no losses. Second property, its windings have zero resistance. Third property, leakage flux is zero. That is 100% flux produced by primary links with the secondary. Permeability of the core is so high that negligible current is required to establish the flux in it. Ratios of a transformer. Now we are going to obtain voltage transformation ratio. We know from the EMF equations E1 is equal to N1 4.44 F5M and E2 is equal to N2 4.44 F5M. Taking the ratio of the two equations, we get E2 by E1 that is equal to N2 by N1 that is equal to K. This ratio of secondary induced EMF to primary induced EMF is known as voltage transformation ratio, denoted as capital K. Thus, E2 is equal to KE1, where K is equal to N2 by N1. If N2 is greater than N1, that is, if K is greater than 1, we get E2 greater than E1. Then the transformer is called as step-up transformer. If N2 is less than N1, that is, if K is less than 1, we get E2 less than E1. Then the transformer is called a step-down transformer. If N2 is equal to N1, that is K is equal to 1, we get E2 is equal to E1. Then the transformer is called isolation transformer or 1:1 transformer. Now we are going to get current ratio. For an ideal transformer, there are no losses. Hence, the product of primary voltage capital V1 and the primary current I1 is same as the product of secondary voltage V2 and secondary current I2. So, V1 I1 is equal to input voltage ampere, V2 I2 is equal to output voltage ampere. For an ideal transformer, V1 I1 is equal to V2 I2. Therefore, V2 by V1 is equal to I1 by I2, that is equal to K. Hence, the current transformation ratio is the inverse of the voltage transformation ratio. Volt ampere rating. When the electrical power is transferred from primary winding to secondary winding, there are few power losses in between. These power losses appear in the form of heat, which increase the temperature of the device. This temperature must be maintained below certain limiting value, as it is always harmful from insulation point of view. The copper loss, that is I square loss, or in the transformer depends on the current I through the winding, while the iron or core loss depends on the voltage V, as the frequency of operation is constant. As losses depends on voltage and current only. The rating of the transformer is specified as the product of these parameters V into I. Hence, the transformer rating is specified as the product of voltage and current are called VA rating. On both sides of the primary and secondary, VA rating remains same. This rating is generally expressed in kVA, that is kilovolt amperes rating. kVA rating of a transformer is equal to V1 I1 by 1000, that is equal to V2 I2 by 1000. 1000 to express in kVA. Full load currents. If V1 and V2 are the terminal voltages of primary and secondary, Then from specified kVA rating, we can decide full load currents of primary and secondary I1 and I2. This is the safe maximum current limit which may carry keeping temperature rise below its limiting value. I1 when it is full load is equal to kVA rating into 1000 divided by V1. I2 when it is full load is equal to kVA rating into 1000 divided by V2. Here we used 1000 to convert kVA to VA. These values indicate how much maximum load can be connected to a given transformer of a specified kVA rating. Ideal transformer on no load. Consider an ideal transformer on no load as shown in figure. The supply voltage is V1 and as it is on no load, the secondary current I2 is equal to 0. The primary draws a current I1 which is just necessary to produce flux in the core. As it is magnetizing the core, it is called magnetizing current denoted as Im. As the transformer is ideal, the winding resistance is 0 and it is purely inductive in nature. The magnetizing current Im is very small and lags V1 by 90 degree and the winding is purely inductive. Here it is represented Im. This Im produces an alternating flux phi which is in phase with Im. Here it is represented. The flux links with both the winding producing the induced EMF E1 and E2 in the primary and the secondary winding respectively. According to Lenz's law, the induced EMF opposes the cause producing it, which is the supply voltage V1. Hence, E1 is in antiphase with V1 but equal in magnitude. The induced E2 also opposes V1, hence in antiphase with V1, but its magnitude depends on N2. Thus, E1 and E2 are in phase. Here it is represented. The phasor diagram for the ideal transformer on no load is shown in figure. It can be seen that flux phi is a reference. Im produces phi, hence in phase with phi. V1 leads Im by 90 degree. E1 and E2 are in phase and both opposing the supply voltage V1. Practical transformer on no load, that is accounting for finite permeability and core loss. Actually, in practical transformer, iron core causes hysteresis and eddy current losses as it is subjected to alternating flux. Practically, primary winding has certain resistance, hence there are small primary copper loss present. Thus the primary current under no load condition has to supply the iron losses, that is hysteresis loss and eddy current loss and a small amount of primary copper loss. This current is denoted as I0. Now the no load input current I0 has two components. A pure reactive component Im called magnetizing component of no load current required to produce the flux. This is also called wattless component. An active component IC which supplies total losses under no load condition called power component of no load current. This is also called wattful component or core loss component of I0. The total no load current I0 is the vector addition of Im and Ic. That is I0 vector is equal to Im vector plus Ic vector. Consider this as equation 1. In practical transformer, due to winding resistance, no load current I0 is no longer at 90 degree with respect to V1 by phi naught, which is less than 90 degree. Here is the representation of phi naught. Thus, cos phi naught is called no load power factor of practical transformer. It can be seen that the two components of I0 are Im is equal to I0 sin phi naught. Consider the equation 2, that is the magnetizing component lagging V1 exactly by 90 degree. IC is equal to I0 cos phi naught. Consider equation 3, that is the core loss component which is in phase with V1. The magnitude of the no load current is given by I0 is equal to square root of Im square plus I0 square. Consider this as equation 4. While phi naught is equal to no load primary power factor angle. The total power input on no load is denoted as W0 and is given by W0 is equal to V1 I0 cos phi naught, that is equal to V1 IC. Consider this as equation 5. It may be noted that the current I0 is very small, about 3 to 5% of the full load rated current. Hence, the primary copper loss is negligibly small. Hence, the power input W0 on no load always represents the iron losses as copper losses negligibly small. The iron losses are denoted as P suffix I and are constant for all load conditions. So W0 is equal to V1 I0 cos phi naught, that is equal to Pi, that is equal to iron loss. Thank you very much for listening this lecture. If you like this lecture means kindly share this video to your friends. For further updates, kindly subscribe my channel. Thank you.